Ok, il audio c'è? Ok, prova. Se. Okay. Thanks, Cesare, for preparing the presentation in little time. That was very appreciated. And now I'd like to let Lyas and Raffaele, who work in our team in Vedrai, talk about their experience working on our projects and sharing back the knowledge. So thank you, Lyas.
Hi, everyone. Welcome today in Vedrai. I want to ask a question in the beginning. Raise the hand for people that know what that means AWS. Okay, Databricks. Okay, perfect. You are in the right place. So, before starting the presentation, let's start talking about who we are. So, I'm Ilyas. I come from Morocco, and I've been working the last 6 years all around Europe in different companies, from startup to big companies to consulting firms. In the last 3 years, I worked for Vedrai and I'm leading the machine learning team. Okay.
Hello everybody, thanks for coming. I'm Raffaele, machine learning engineer here in Vedrai. Before getting to this stage for working for Vedrai, I graduated in Politecnico di Milano in computer science and engineering. Then I worked for 2 early stage startups. The first one was SmartFab, in which I played the role of data scientist and machine learning engineer for to build this product for predictive maintenance for manufacturing companies. Then DRB, in which I focused mainly on computer vision for autonomous drive of drones to inspection of wind turbines. And then I had also a consultancy experience in Vedrai as data scientist, working mainly for companies in the field of energy industrial.
Okay, so we present ourselves, and now let's present the company that we work for. So what is Vedrai? It's a startup company that was founded in 2020. Like Rijal has already talked a lot about the company. We'll duplicate the slide. And yeah, I forget to say that we are more than 80 people, and we raised more than 40 million. So that's it. Our mission is to democratize the use of AI for all company size. So this is very important. It's something that we keep in mind each day. Okay, what is our position in the market? So what we provide as a value. Vedrai is something that provide perspective and insights as an output, as a value, as a product at the end. So what that mean? So we are not just like answering the question what will be in the future or what may be the future, but we are also responding to the question what I should do, what the actions that I should take. So this is exactly what we provide as a value. And now Raffaele will talk exactly about our product.
Okay, so our product is divided in 3 main verticals that are partner platform, in which we use it mainly by the clients and by system integrators for setting up the decision problem. So in this, using this tool, the client can compose a DPM, we call it DPM, decision process map, in which all the information, the internal data of the client, along with our market data that we provide to the client in order to provide a full picture of his decision problem. So he can compose this, setting up this problem with all the linkage with this data. Then this information pass through the second vertical, that is PAF, that is the acronym for Prescriptive Analytics Framework, which is in turn composed by other two main parts, Data Factory, in which these data are integrated, processed, and served to Vedrai Magic, that is the computational flow of our solution, in which we simulate all the possible futures of this variable, along with also performing computation for providing prescriptive analytics. Then these results are served to Vedrai Suite, that is the front end of our application. It's a very customizable front end, like we can see from a snapshot in this slide. The client can, the decision maker can select this widget, customize, choose from plots or numerical widget, but also natural language processing widgets that explain better the solution and the solution proposed. And it can also interact with this tool, like creating scenarios, what-if analysis, in order to have the whole picture and take a very informed decision.
Okay, now we will start talking about the serious slides. We are just talking about the slides that put Ricardo, and let's start talking about the things that matter.
Matter to us technical people, are very nice.
So we will focus more on the Vedrai magic part because we assume that the data factory part is already working, and like that's Christina promised. So before start talking about the problems that we had in Vedrai, let's talk about the model lifecycle in general, and then we can, from that, see exactly what's the common challenges that we can have, and see exactly how we will fix these problems. And then at the end, we will understand that we still have a lot of problems to fix. So let's start from data. So we have clean data that Christina provides to us. And from that, we need to make a lot of features engineering processing tasks and collecting the data from different time series. And at the end, we need to create the payloads or configurations to start or run the machine learning part. So if we see this description, we can understand exactly that the main problems in this task is the governance of data and the scalability of the processing jobs. So once we have the data frame ready and for the machine learning training, so we pass to the next step is the model building, where we try to create a lot of possible models and then select the best one and deploy the best one in production. So if we see exactly the challenge that we had here is the part of tuning, especially when we are selecting different models. The part of scalability, because we are running lots of parallel jobs, and the part of model governance, because we need to log all the parameters and important informations of metrics and artifacts of the model in some unified place. So in the last part, putting the model in production, have two main challenges. The scalability, because if the clients that will ask for inference is like making lots of requests, we need to scale with them. We're not forgiving, for example, many requests error or something like that. And the second challenge is the serving part, because each use case has different serving strategy, and Raffaele will explain very well this part. So this is exactly the main challenges that we have. And at the end, doing this cycle for each model, for each month, for each day, need to be monitored and debugged, logged. So what are the solutions? What we did as a task or work for resolving these problems. So before starting talking about the solution, we want to also talk a little bit about technical stack that we have, that's the technology that we are using or choose to use. So first of all, we choose to use AWS as a cloud provider and all serverless services. For example, Lambda, Fargate, Batch, Glue, all what is serverless, we choose it. And, and as a partner of data, we have Databricks. So Databricks is our partner for the parts of data. And Databricks provides two things important: the Unity catalog that is unified and centralized, and the self-hosted MLflow version. So we don't handle like the MLflow server is already managed by Databricks. For the languages that we use mainly Python, but also PySpark for the distributed computing. And for the machine learning models, we use lots of open source libraries. So we see the problems. We already see the technical stack, how they fit together. So let's start from the data preparation. Here, the problem was the governance and the scalability. Using PySpark, we can make distributed computing, and we can handle a large volume of data. So that will surely help. For the part of model building, we had scalability, tuning, and model governance. So MLflow is collecting all the experiments and track every job. AWS providing us the scalability using the serverless services. And for the part of tuning, so we are using the open source models that can help us, that have lots of hyperparameter functions and metrics. At the end, for the part of deployment, so we used, for the moment, Docker for the container, for the part of container, and replicating the same results, and Spark for the part of distributing. Raffaele will explain this part very well, so don't panic. Okay. Machine learning. When we say machine learning, so it's training part and inference part. I will talk exactly about the training architecture, the training platform that we build. Raffaele will, again, speak about the inference part. Another presentation, Raffaele. So I would build the architecture. So let's see here. Our customer or the person that triggered the training platform is the partner platform. It's like a backend service. And this backend just send us a message in a queue and told us, OK, this is this client that have this variables and only provide the names and this granularities. Make me models. And from other part, we have Vedrai TS, our class for machine learning, that need a very clear requirements or a payload in the input. So there is a big gap here. And this is exactly why we build Mind the Gap as a service, a kind of function service that we choose to do. But Mind the Gap needs to have efficiency and robustness. And given these two words, we think about Ibrahimovic. So we call it Mind the Gap for that reason. OK. Didn't work the joke.
No, I want a beer.
OK. What does Mind the Gap? Ibrahimovic is the sponsor of the Mind the Gap, is like the product.
If you explain the joke, it's forced.
OK. So Mind the Gap, what does do as a functions? So collecting the data for the partner platform, assuring that have the right access, like the policies, assuring that the time series are clean and ready, and create all the configurations, different configurations for different models that I will run now. Let's give an example. I don't know if it's clear for everyone. So let's say partner platform is a backend, is the part of the backend. Told me, I'm Burger King. OK, Burger King is clear for everyone. OK, I'm Burger King. I would like to know exactly the forecasting of my revenues for the next month, no? Or next 3 months. So partner platform just told me this message. Provide me forecasting for the next 3 months for my revenues. This is exactly the message that's come to us. We need to go to each time series of Burger King revenue as a variable, for all days as granularities, months as another granularity, and for all stores of Burger King in different locations. But we need to add covariates, like weather, events, and the covariates that the clients choose in the DPM. And we need to collect all this stuff. So this is exactly what Mind the Gap do. And then when we collect the data, we need to create the configurations for all models that can work for this use case. So we need to provide ARIMA, Prophet, some deep learning models, and so on. So this is exactly what Mind the Gap do. And then as output, write all these configurations in a queue, in this queue. To Vedrai TS, that's another step function, another workflow. And Vedrai TS run all the models in parallel, choose the best model, and log all the information about the best model in MLflow. And response a success message for the deployment model. What do the deployment model is the part of serving. So it's collect all this model, all these models. OK. So I was in this part. So when we arrived to the serving part, And from here and then, let's see exactly what's in the background did the Vedrai TS and deployment model. So we have different models. It's like ice cream, different flavors. We need to standardize them by rewriting what that's mean, fit, and predict, and tracking all the running. So we need to track the parameters of the model that we put in input, the metrics that we have in output, the artifacts itself, and then write exactly what that's mean model, MLflow model. So write exactly the functions that we need to start for the predict, for the train, and so on. And write the part of the Docker where is it present exactly the environment or where the model will survive. Once we write this part, we need to deploy the model using the registry part. So the registry is a kind of service that or function that help you in MLflow to associate for each version or stage. And you can have different stage and say exactly, okay, I will put it in production, and you can go on. And the last part is the model serving. From here, we start like the parts of inference, and then Raffaele will speak it very well. Finally.
I will explain this part very well. Finally. The hype grows. So, Elias explained very well how we train. So now we will explain very well how the models are served. So how can we serve AI models? There are mainly three ways. The first way is a more common way. It's the batch inference. The batch inference pattern is used when we have all the input data at the very beginning, all available. So we have many information about this data. We know the schema. We know the amount of data. We know when this data, fresher data, will come into the system. So these allow us to perform a very efficient computation, both logical and resource-wise, because we know all this information, so we can tune the solution, the prediction task accordingly. This kind of batch inference has high throughput, so but at the cost of high also latency for the single prediction. And another disadvantage is that we need to master usually diverse technologies in order to implement a very good batch inference with paying also a cold start period. The second kind of inference is the real-time inference. We usually, the main difference is are two. The first one is that we don't have all the input data available in the very beginning, at the first moment, but we have this input data on demand when they are needed. So we can imagine an application, a client that performs some operation on the application. With a tap, it sends a request. Usually, this request goes to a web server, and then an AI model under the hood perform the prediction and send it back. This is provide a very quick response, so near real-time response with so low latency. The resource used are lower than the previous case. The throughput is low too, and there are some limitations. Like usually there is a limit of concurrent requests that can be performed so concurrently in parallel, and the cost per request is higher than the batch case. Finally, we have the streaming inference, that is something between the real-time and the batch inference. It has very high performance. We can obtain high throughput and low latency with this kind of prediction. We can see some similarities with both batch and real-time. We have a streaming service instead of a web server, so there is a communication protocol in both cases. And we have a AI model with this little image that represents something resource intensive. So we can perform high parallelization, high resource utilization in order to attain these performances, but this comes with a cost, obviously. The cost is the streaming service, so it has a cost itself, sometimes high. The configuration of this service is more complex, and we also need to manage many technologies, more than the other two patterns. So these are, okay, this is a summary table, photo moment. 5, 4, 3, 2, very well, okay. So, how do we do predictions in Vedrai? So, what pattern we use, what inference type? All of them, because we need to do everything. So, of course, this has a sense. We selected the correct model, the most fitting inference pattern for each use case. We use batch inference for our market data, so because the requirements are very clear. We have this data at the very beginning of the pipeline. We know exactly how much data we need to handle. We know everything about this data. So how did we implement this pipeline? We have a cron job, maybe a bridge that trigger a job workflow on Databricks. This workflow runs on a cluster that we tune accordingly to the market data that we need to predict. This cluster, on this cluster we installed a Docker image with all the dependencies. We use MLflow to load the models onto the cluster, and PySpark SDK to distribute this prediction over the cluster. We read the input data from a Delta Lake that is hosted by Databricks and write back the prediction on the Delta Lake in another catalog. So very linear, but simple sometimes is the best choice. Then we have real-time inference. Real-time inference is used in simulation engine. Actually, this was maybe the most interesting things that I worked on with lyas in Vedrai. Because it was a trip. We started from real-time inference simulation engine. To recall this, it's the core, computational core of the solution that has the purpose of simulating all the possible futures of our variables. So each, in order to have the future, we need to predict and use AI models that we train very well. And so the first moment we deployed serverless real-time endpoints on Databricks, and we send requests to these endpoints that was managed completely by Databricks. We just provided Docker file for the dependencies, so we deployed the model with MLflow, we register it, and under the hood, the serverless endpoint goes to load this model and perform predictions. So that worked in the beginning. Then when we start to send many predictions, starts the issues too, because the simulation engine was much faster than the endpoints. It was much faster to produce the input, the payload, than the endpoint to produce the predictions. So there was a mismatch. This provoked errors. We were like DOSing the endpoint, so providing the denial of service for the endpoint, and this provoked error sometimes. Then there is also a limit, as I said before, on the number of parallel requests that we can send to an endpoint. So we thought about a solution to slow down the simulation engine. And we got through this solution, that is the token bucket. Token bucket is a very common solution for this purpose. So but usually it's done on a time rate. So you can define how many requests per second, for example, you can send to an endpoint. But in this case, we had a very specific limit on Databricks. We have 64, for example, open requests. So what we did, it was to revisit this architecture, thinking, okay, we have a bucket. Every time a simulation engine sends a request, we put a token in this bucket and reserve a spot. If the bucket is full, the simulation engine waits and keep checking the bucket size. When it's not full, we put the token, as I said, we send the request, we get back the prediction, remove the token, and free a spot for a new prediction. So this worked. As that makes sense. So we solved the problem, partially, because the performance, of course, were not acceptable sometimes, since we are slowing down something that can go faster. So it's something that we don't want usually. And also, this was a very big problem. The token bucket architecture that we revisited was full full of technological components. We have DynamoDB tables with streams, we have SQSQ, Lambda. So it's a microservice architecture, and it's very hard to keep the consistencies of all the services when there are failures or so when there is a success. So we decided to get to the streaming inference. Region loves streaming.
How much does it really cost?
Never mind. So we used as streaming service Kafka, and we deployed it through using Amazon AWS MSK, that is the Amazon managed Kafka host. So what we did, we moved also the prediction part onto a database workflow. That is, if you recall the image of the previous slide, it's very similar to the batch one. So we use the workflow, we store the image with the dependencies, we use Spark and MLflow to distribute predictions. But this time, we are not reading a data table, we are reading a topic stream. So, a topic and stream. So, it's read the request faster, we decouple the two entity. We read the request from the stream and write the prediction back to another stream. So simulation engine can go to the velocity that you want, the same for the workflow, and we can get the maximum performance. So the results, 10 times gain in computation. It was, we went from a run of an hour and 20 minutes to in which the prediction part was kind of a small part of was the biggest part of this. We went from 60 minutes to 6 minutes of prediction. Then the other part is cold start, the other processing of the simulation engine. And we have problems, not really problems, just attention point. Well, maybe one problem with the price, but this can be another topic. So we carried on some things to do still. Maybe optimizing the publishing part of the messages on the simulation engine to be more effective. There are many clients library, and we are still finding the differences and the best one. We need to configure the streaming host in the best way, provisioned, or also migrate to serverless if it will be needed. And then we can optimize the computation part. There are many considerations on this topic. The partitioning to distribute the work on the cluster. We can reduce latency in some cases. So, and we have to do this all keeping in mind the cost. So under control.
But the cost is not really a big problem.
Because you don't pay for that.
No. So at the beginning, maybe the serverless parts will cost you less, but once you have lots of clients, lots of use cases, and they are running in parallel, streaming will cost you less than the serverless part.
Sure. That's it. Conclusion.
Okay. Thank you for explaining very well this part. So let's talk about conclusion. So we start talking about one of main challenges that we have, that is the governance. So we don't have one unified centralized part to handle our models and data. And with Databricks, using Databricks and Unity Catalog and self-hosted MLflow, we control this part. We had the problem of scalability. We are in conclusion. We have a problem of scalability and using distributed computing and Amazon as a cloud provider with parallel jobs and serverless services, we try to handle this part. For the governance, using MLflow, we can track, log, serve, deploy, register the models, and we can handle also this part, Unity Catalog, all the time in Databricks. For the AI serving, we, Raffaele, explained very well the strategies that we have, the different strategies that we can use, and the only things that we need to keep in mind here, that all the time it will be a solution. It's not straightforward, but it depends on the use case. All the time we can find something. So we didn't like resolve all the problems that we have. It's still a lot of things that we need to do. So as future work, we would like to introduce and start working on Future Store for the market data part, and also working on data drift, concept drift, and model drift when occur. And to do that, we need like more colleagues in Vedrai, and this is exactly what we're here. We're looking for new people, and thank you for coming. Questions? Microphone.
Hi. So I have a question in two parts. The first part is when you do batch inference, how do you choose what to inference about? I mean, I guess you have a standard set of things you usually predict, plus the requests from the specific client, or how does it work?
No, we have.
Okay. Now, market data are fixed, so there are not client data. There are data that Vedrai are an asset of Vedrai. We buy it or from some sources, data sources, and we provide them to the client. So we know exactly what these data are. They are not the data is not coming on request or on demand. They are loaded in a regular time basis. So we know exactly what we are doing.
So you don't load any client data?
Yes, but the client data are pre-processed and processed in Data Factory, then are made them, the historical data are ready on Data Factory. Yeah, we can retrieve the image. Then this data, the client data are taken, are loaded in the simulation engine that perform request on demand. That's the main difference. So for that case, we in the first case with the market data that we use also in the simulation engine, we pre-compute the future. Instead, for the internal data, we pre-process the data in our data factory and then perform some simulations and compute the distribution of this data. So then we send a request on demand on a variety of features that we can use for then the prescriptive analytics.
Yeah. Okay. So the second part of the question is, since you have to predict what the client is going to ask you, I mean, are you working on that to minimize the workload? Because I mean, there are thousands of possible questions that the client will ask you. Are you trying to predict them in order to lower the workload you will face?
Okay, so the possible questions are bounded somehow because we have in the setup phase. We had the three verticals that I said to you. The first vertical is the partner platform of the product in which the decision problem is set up. So in that case, you know exactly what are the data of the client, what are the market data, proprietary of Vedrai that are involved. So in that case, you have this data, and the client can, through the third vertical, that is the Vedrai suite, can open objective. For example, if its data is the revenue, it can say, I want to have this revenue. What are the actions, for example, that I can take for reaching this revenue, or with the actions that my strategy, what is the possibility that I can get to that revenue? What is the probability? So from that problem, you can set out, so the questions, if we can call it in this way. And then through the simulation engine, we computing distribution on the internal data and performing some variety of combination of samples of these payloads that these variables that becomes the payload of the models. We can predict many futures. So in this case, we have the database also in the future in order to perform the prescriptive analytics that, as Ida said very well, are what we can do to reach our objective. So this is I hope that.
So the client has to be, I mean, cannot ask anything. It has to be a question
Actually,
related to the one of the first objectives that they set up at the beginning.
Yeah, but you can. The setup is flexible, so it's kind of flexible. You can perform any. This is the power of our solution. That is the flexibility. With this decision process map, we can. We don't have really boundaries to the structure of this connection of data that we can do. So it's very flexible, and more or less everything with some limit, of course, that comes can be defined. So you're welcome.
Other questions? I have one question. You showed us a lot of technologies. You showed the full stack you use. What is the part of that stack, the technology that you cannot live without?
Databricks.
Okay, let's go to this.
And why?
Okay, I will take this one. Okay, so mainly the serverless part is for all the training platform. So without these services, we cannot train models. Okay, the Databricks is for holding data and running the clusters for the inference. So without Databricks, we cannot do inference. We can survive only with one model, like putting only ARIMA, and be happy with that. We can survive without MLflow, but if some things like go wrong, like for example, some new version of the model or something, we will not launch that. So MLflow will help us with that. Python, so we cannot survive without the code.
Right question.
So we can have like different cloud provider, we can have different competitors from Databricks, but
Can I add a thing to that question, to the answer actually? Because yes, definitely it's Python, the part of the stack that we cannot live without. Now, Raffaele and Lyas explained very well the part which is, you know, the central brain that imagines the future, the possible futures on which you can base your decisions. But then we have all the product layer, right? The kind of customer facing, the client facing part. And the cool thing about Python is that we can use one language in all the various departments, in all the various roles, you know, across the stack. We all speak the same language. It's our own lingua franca, so to speak. So that gives us the power. We can build a web application in Python. We can then, you know, load data, express the business logic, you know, do all the training all in one simple language, which is fantastic. Now, there's the front end. Okay, and there are no front-end engineers here. We do have front-end engineers.
We can say that you cannot do the same with Java or C or C#.
I don't think so. No.
okay.
Elias, what's your opinion?
Like there is lots of research, for example, to build new models for machine learning, and lots of researchers all around the world, they are using only Python for the moment. So we will have lots of difficulties to find open source models, new open source model with different languages than Python. PyTorch is working very well. So going to use Java for building models and trying to do everything from the beginning, good luck.
Yeah. Any other question? No? That's it. Thank you again. Thank you.